this is the reaction that we're gonna perform these IRC calculations for. It's a methylene chloride with a fluorine anion reaction to form methylene fluoride with a chlorine anion. And so here you see the transition, the transition state of such chemical system. So as I mentioned, or I may have mentioned in the YouTube description, this methodology would be for basically doing these calculations with using Windows system alone. However, you may need to install a couple of programs. The first program that you're going to need to install is the Orca compiler for ab initio calculations. And the second program that you're going to need to install may be Python if you don't have it already. Several of my videos show how to install Python. And that, I think, it's basically it. It also helps if you have already installed the Atom interpreter, as well as the Git bash system. And all of these different programs that you're going to need to install to make these calculations very easy, I'm going to place the hyperlinks under the video description so that it's easier for you to follow and install everything. Nonetheless, so I'm just going to go through the Orca installation because this one is the more tricky one, I feel. So for the Orca installation, what you need to do is you just need to go to the Google website, and then for your keywords are going to be Orca, as in the whale, right? And then forum as the second keyword. And then after you've searched those keywords, right, it should be the first result that comes up. Okay, so you click on that first result, and then you don't go to downloads. You need to actually register. All right, so there should be, not here because I'm already logged in, right? But there should be a login option here for you and register. You need to register, and then because if you don't register and you go to the download site, you're actually just gonna, this is what you're gonna get. You're not gonna get any available downloads of the Orca program, right? So nonetheless, so this is why you need to register before you install or use the software. So after you've registered and logged in, you will actually, if you click on downloads, right, it will actually give you this site. It will show you several packages in contrast, right, with nothing here. So I mean, as I mentioned, this video is more like focused on Windows operating systems. However, you can follow the same guidelines if you have a Mac computer and just install the corresponding file here, right? If you have a Mac operating system or Linux, right? So if you have a Mac, I think it's probably Linux may be compatible with it. But nonetheless, so you may, if you have a Windows, it's 64-bit operating system, you will install this. I think there's even some specific options for Mac operating systems as well. Fortunately, if there's no option, I haven't checked, but if there's no option for 32-bit Windows operating system, I guess what you can do is you can install the Linux version, and then just use. You may need to Google or type here Microsoft Store, and then type keyword search Ubuntu, and it will so you can install an Ubuntu emulator through Windows. I actually have one that I actually downloaded it from the App Store some time ago, and it's pretty handy. It's this one that I'm showing here. Right. Nonetheless, yeah. So if you had a Windows, going back to this, just install the latest version, 64-bit installer version. You're gonna click here, and then just click on the big green button, download. All right. After you're done with the installation, you're gonna be eager to find the Orca program, and if you're expecting a standalone file, you may be a little bit disappointed because there's no standalone file. So what that means basically, right, is if you type Orca, and it will actually give you an application, right? But if I click on it, it's like there nothing popped up, or something popped up and disappeared really fast, right? So Orca is actually has to be run through a command terminal, and I'll show you in a few how to do that. Um, before doing that, however, right? So I need to show you basically. This is actually going to be most of the bulk of this video is going to be following guidelines from a specific website from Orca, right? So what you're going to do now is you're going to, after you've installed Orca, you're going to Google Orca input library. Okay, and Orca link input library is actually a Google site. You're gonna click on that, and now we're gonna go to the tutorial here, saddle point TS transition state optimization via relaxed scan, and this is gonna be now basically the bulk of this video is now gonna be on basically a walkthrough of this tutorial. Actually, a very brief or very fast walkthrough of it. And we may actually not be performing all the different variations on all the different methods that they have to calculate transition state, this transition state optimization. However, it's going to be a walkthrough nonetheless. Okay, so I will also be placing this link in my video description so you can find it really quickly and have no problems following on your own as well if you want. Nonetheless, what we're going to do now is we're going to be, as I mentioned, following this this document, right? So we're actually going to be this the documentation here. The documentation here it shows that they're actually want to use the semi-empirical method of PM3, stands for parametric method number 3, to run these calculations, right? So semi-empirical methods are not very accurate, as they mentioned. They're cheap because they're actually using equations to approximate the integrals that are needed to describe the orbitals of our molecular structures or the molecular structures in interest. Nonetheless, even though they're not like 99% accurate, sometimes they're very helpful and handy for us figuring out what is going on or comparing them with different systems. At least here, right? So of course it's telling us also that if we want like some to make production calculations, it should be done at a higher level of theory and not semi-empirical methods. If semi-empirical methods are used, right, there needs to be a type of confirmation to show that they're actually accurate or in comparison, or very accurate in comparison to higher, more higher level of theory methods. Okay, so here is just like outlining of what are certain some of the steps that all of these transition state optimization methods follow, like the relaxed surface scan, right? So they're actually going through method number 1. It would be using relaxed, have to be where you would have to explicitly do relaxed surface scan, as well as, right, and then as well as doing an optimization close to the point of the transition state that it can be obtained from the step number 1, right? And then also using an exact Hessian, which is basically all the mathematical interpretation of the transition state expressed in a type of tensor differential operator, tensor representation. And nonetheless, right, so what we're going to do is we're actually going to be going with a more modern strategy or method, or I would say modern, quicker method, because there are methods that are far more superior than this one. Nonetheless, because of the limitations that I have with my current computer and everything, I'm actually going to be doing a PM3 variant of this notch, like this elastic band algorithm. So what's really fun and cool about this algorithm is that it only requires uh, us to specify the coordinates of our input of our reactants. So basically, the locations of the reactants with respect to a reference molecule, as well as the coordinates of our products, right? We also with respect to the reference molecule. So that's pretty cool because that's all basically that you need to specify to obtain these transition state barriers that we desire. And of course, if you look at the input file, because we need an input file besides the the coordinate files that I mentioned, the input file is just specifying what method is we want the program to use. And so it's just specifying at which level of theory we want to do the SCF calculations or self-consistent field theory calculations, and then like also what specific algorithm we want to use for transition state optimization. And so other information is we are also having information from the product coordinates and the reaction coordinates. Okay, so and this is just basically telling you, giving you some information of what the output may look like. Right, so the NEB CI is actually a variant. I would say a superior one of NEB alone. So what CI does, it says it's a climbing image variant of NEB. It's superior only because basically it makes the computation much faster. So it makes the whole methodology is more efficient than the NEB alone. It uses constraints that are a little bit more relaxed, which is why it gets to the solution faster at the expense of a little bit less accuracy. However, if you want to go into something a little bit more accurate but still fast, you may use the NEB-TS, which basically sets up some the constraints are a little high at the expense of a more you get like results that are a little bit more accurate at the expense of a slower computation time because the constraints are a little bit tighter here in certain instances of the calculation. And nonetheless, what we're gonna go with is we're actually gonna be going. Just looking at the time. We're gonna be going with the PM3, this semi-empirical notch elastic band climbing image variant. So this one basically, right? NEV CI job. So the first thing you need to do is you need to calculate. You need to copy, the commands here and save them as an input file. Okay, so what I'm gonna be doing now is I'm gonna open Atom, my handy text editor. Okay, just sorry. My handy text editor, Atom, and I'm just gonna create a new file, and I'm gonna be pasting what I copied from that page, right, as I showed you, and I'm gonna be saving it in my Orca folder. You should create a folder where you have all your Orca files for these calculations. If you haven't already, you should do it. Okay, so I'm gonna place them here. I'm just gonna call the file. I'm just gonna be calling it a ch3. So basically, just I guess I don't want it to make it too complicated, right? So I'm just gonna be calling it a PM3, as in the semi-empirical method. It's gonna be also, what am I doing? Notch elastic band, and then I guess CI. Okay, and that's gonna be the name, and .in. It doesn't require an extension, but it's always fun to have an extension. Just make it cute, right? And we're gonna be actually creating a folder in this directory, and I'm gonna be calling it, actually the folder is gonna be the basically methyl F. Okay, I said that would be the basically the product, right, of the reaction that we're analyzing. So I'm gonna place that inside that folder. Okay, so I created that file. That was easy, right? Now, for creating the other files that we need are going to be the reaction coordinates and the production coordinates. And now you may ask me, right? And you may ask me, Andrew, like how are we going to be generating those files, right? That all looks very complicated and whatnot, right? Like getting all the coordinates for the molecules. Well, it's very easy. You just need to install Avogadro. Actually, you may need to install Avogadro as well for this, and you're going to be creating your molecular structure here. I'll also place the link for Avogadro on my video description. I apologize about that. I forgot, about this program, the need of this program. So the first structure is basically this, right? It's chlorine, methylene chlorine. So methylene chlorine, I'm just gonna start with adjust hydrogens and draw it. And if it's methylene chlorine, it's gonna look like this. And now I'm also gonna add a fluorine group, and I'm gonna add it here. Okay. Now there's a very handy tool in Avogadro, which is this auto optimization tool, and that will basically give you equilibrate the system so that it gives you a more likely configuration of the molecules and their space with respect to other molecules or atoms. I'm just going to start, and you see a change, and then this should be a very more accurate representation of that molecular system. Okay. So after you've made basically build the reactants and how they should So this reactant system, right? What you're gonna do now, you needed the coordinates of this system. So you're gonna go to extensions, and you're gonna go to Orca and generate Orca input. Okay. And basically, this is where you can get your coordinates. All of these should be your coordinates. So you're gonna copy that and create them, make them copy them. I guess like you may need to copy a couple of these lines as well, and you're gonna need to make an input file in the same way, in a similar way as this one, and place it on the same folder, right? Fortunately, this example comes with some templates here, some XY zeta coordinates for that example already. So I'm actually going to be downloading and showing you how they look. So React and product. And I'm not sure why we need this one, but I'm going to download it anyways. Okay. And now what we do is after we download them, right, it would be good to move them also to that folder as I mentioned. So I'm going to be moving them. I'm going to show you what they show. I'm going to show you what they show you what they have inside. Okay, so basically, I hope that this works. That didn't work. Oh, yeah, never mind. It did. So I copied them from my download folder to this folder, right, that I created. And now if I click on any of those, they're going to show me what these files have inside, right? So the reaction coordinate, it's actually very similar to what I showed you here in the atom, in the coordinates that we created using, sorry, not atom, Avogadro, right? So our Avogadro generated coordinates were this, and the coordinates also that were given as templates for that same system that we're analyzing are basically, they look like this. So they have the same layout. So I wouldn't be surprised if they actually used Avogadro to build the system, right? So anyway, so now if you ever have the need of getting molecular coordinates, this is a really easy way of doing so, of getting them. So, and product coordinates also look similar, right? Have a similar layout. This would be basically the coordinates for that side. And then these, and this is a file that you may actually not need now that I look at it. But nonetheless, we'll just leave it there for the time being. We'll just leave it there. We're not going to use it, but it doesn't matter. It's not going to hurt the program. Okay, as I mentioned, we also have our input file. And that's basically what it is. That's what it is. That's all there is, I mean. Okay, so now after you've collected all your files, you're going to run it using Orca. And now this is where the magic happens, right? So you're going to open a terminal. And here I have PowerShell, but you can actually use the command prompt. You can type .cmd command prompt and use it. I'm just going to use PowerShell because I'm more accustomed to it. But the same process would be the same process for if you just use the regular command terminal line. All right. So first thing that we need to do is we need to go to that directory where I'm placing all my files. Okay, so that directory, I'm going to access it really quick. Just a second. Yeah, time is going. Time. So I'm going to change my directory to, I hope that I'm in the right place. Yeah, it would be methyl. Okay, so now that's all my files. You can see I have the same files in there, so I'm in the right place. So now after I've jumped into the directory of my input file and my other coordinate files, I need to run this optimization, this transition state optimization, right? So how do I do that? It's very easy. I just type Orca, followed by the input file, which is pm3-neb-ci. Then I do this less than sign, I think. And then just results out. And then results.out is just the output file basically the file where I want to store all the results, okay? So it's as easy as that. Just typing Orca, your input file, and then a name, any name that you want to give to your output file, okay? Then you press enter. And as you've seen, it started to populate that folder, right, with a lot of files. That's because it's doing the calculation right now. That's pretty cool, right? So it's gonna go for some time. You can see the results if you're interested, and if you click on results.out, right, and it will actually start populating this text file as it goes, as it computes, as the program runs. I'm sorry, I mean, right? So it's running a little bit more. There's also another file here which is helpful. I forgot what was the name. Just a second. Anyways, as I mentioned, it's gonna be a little bit of a slow process. So what I'm gonna do is I'm gonna show you what the output will look like after this whole computation has been completed. All right, so just bear with me for a second, and in a few I'll show you actually what the output should look like. But actually, while this is doing that, I may actually need to show you. No, actually, let me just go with that. Let me just show you what the final output will look like. All right. So I'm going to pause my video for a second. All right. So this is basically what the output will be after you've after you've waited for the calculation to complete itself, right? So there's two things to look into here, to look at here. One is the log file, which shows you the results for every iteration that it does. Right, so it's done it, I think, 15 times, so 15 iterations, and this is all the information and energetics of every one of those iterations. And now, if you look at the basically our output file, right, that we named the results that out, then this is basically also some very important information that you may need to interpret the results. Okay, so if we go, sorry, if we go downwards, it's going to show us, it's going to tell us, give us a statement here where it says that the NEB optimization has converged, right? So, and it's telling us that it has converged in 15 iterations. All right, so as I mentioned also, as I might have mentioned, right, the log file shows us gives us a lot of details about the energetics of our system at every iteration. Now, it may be good to actually interpret the data or process the data in a more graphical way, so we can rescue some good information from what we've obtained here. So doing so is not very complicated, but you may need to install another program from the programs that I've shown you already. So we're gonna go back to the internet here, to that manual that I was doing the walkthrough of. And basically just gonna go to, I'm sorry, I'm just looking at the time, to NEB tutorial here. And now I wanna get these pretty plots, right, that you see here. So a visualization of results, right? Like I can see also, like, you can obviously, from your results, you can possibly make animated renderings of the results, right? Like, such as these two, which are actually, they're cute, right? But I'm not going to go through that. I'm just going to go through the visualizing the energy barriers, transition state barriers. Right? Even though these are kind of nice though, right? But I'm just going to go through the basically how to generate these plots, which are very helpful actually in giving you a sense of what the transition state would look like. Okay, so in order to do that, right, what you may need to do is you need to go to this GitHub address and install this Python file. Actually, either install it, clone it into your computer, or just like copy paste the code. But as I mentioned, if you have already installed, you have installed Git Bash, as I've told you, and I've shown you on the links, as well as Python, right? You shouldn't have many problems importing this code. So first thing, I'm also going to place the link of this site so that you can install it easy. Basically the importing of this code is very easy. Nonetheless, what you need to do is click on clone here, copy that address, and now you're going to go to your terminal again, and you're going to go basically, if you have a place where you actually, I'm gonna clone it into that Orca folder. I think that would make it nice. So basically, after you copy that address, what you're gonna do is you're gonna find the path for all of this code for that repository that you're cloning. So I'm just gonna go up one directory, and I'm gonna be actually at the Orca direct path right now. Now what you're gonna type is you're gonna type git clone, and then you're gonna paste the address you copied. Okay. So after after that's finished, which was pretty quick actually, you should have the NEB visualize repository cloned now into your path. So you can just type dir and you'll see that you have NEB visualized now inside Orca folder. Okay, so now how do we use NEB visualize, right? Well, thankfully there's a README in the repository, as there always should be. And this is their use. They're showing the usage here. It's very easy. Basically, you type in the terminal Python the name of the code, which is NEB snapshots, base name interpolation. This is the file that you actually, one of the files that was generated in the Orca, with the Orca software. It's actually here. I think it's this one, if I'm not mistaken. No, it's this one. This one. Okay, and then the other two arguments are the iteration that you want to start at to plot, and the final iteration that you want to plot. So that's very easy, right? So what I'm gonna do is actually, I'm gonna copy that address, copy that command, sorry. And now I need to go, I need to execute it inside that NEB repository, right? Otherwise it doesn't work. So, and of course, I'm just gonna go inside that repository now. I guess it's the best thing to do. And the files that I have there as NEB, snapshots, and README. So I'm just gonna paste those arguments, right? So what we need is, basically we need now the interpolation file and the start of the iteration and the end of the iteration. If you remember, right, from the results.out file, it told us that it converts after 15 iterations, right, if I'm not mistaken. So we're gonna type that right now, 0 and 15. But we don't have the interpolation file in this folder, so we need to import it into the folder. Otherwise, it's just going to give us a mistake. So I'm actually going to go now and import that file. The name of the file, I'm going to make a copy of that interpolation file, right? Inside this folder, inside the NEB snapshots repository or NEB visualize. And doing that, I just need the name. Once again, I need to remember the name of that file that we need, which is this one. So I'm gonna just copy that file name. And now I'm gonna, after I copy it with Control B, I'm gonna do a terminal copy of that file in that path to this repository. So cp, copy the name of the file. It should be, sorry, just looking at the time. Right, and I'm gonna be copying it as just into that folder. I guess I can give it base name. The name could be base name dot interpolate. It would still be copying the same file, just change the name to base name. So I'm gonna do that. So now if I look inside my NEB visualize repository, I will find that file copied with a different name. That PM3 NEB CI whatever, it has been copied and renamed as base name dot interpolate. Okay. So now going back to the command line, command argument, in order to make that graph, I would need Python to type Python NEB snapshots, which is the name of the Python code, which is here, and then the name of the file, interpolation file, and then the iterations that I want to plot. I'm going to be plotting, from the first iteration to the 15th iteration. So that enter. looking at iteration 0 to 15, execution terminated, see NEB frames. Okay, so now if I look at my folder, the insides of my folder again, I'll see that it's created a new directory, which is NEB frames, and that's where basically our graph should be now. I'm gonna go inside it. And as you can see now, these are the two name of the files that have been generated from this code. Right, so we'll take a look at the first one. It says NEB's last iteration.pmg. Just gonna open it. You can see that's the, so as you can see, last iteration is the lowest in energy, right? Basically, the variational principle is telling you that the accuracy is improved as you obtain lower energies for your system. And iteration 14th is actually one of the lowest, if not the lowest, of all of the iterations. So this would be the most accurate one for our system. So I guess this is the end of the video. I was actually, oh, and of course, if you want to also interpret, right, what is HA, right? These are actually heart trees, which is also a unit measurement. Sorry, unit measurement, an energy measurement, right? And bores, I think they relate to the bore radius, and this is the displacement. It's just the reaction path. All right, so this is the end of the video. So thank you for watching. I hope you found this helpful. I hope that you can also find it helpful to adapt it to different molecular systems or different chemical reactions. And if you found it really applicable and you liked my videos, or you like my videos, and please click on subscribe. If you like this video alone, please give it a like. And thank you for listening. And that's it. Bye.